Welcome to this video at 11th hour. This video is going to be about design of a full adder with the help of three variable k-map, and we are going to see how we can use two half adders to build one full adder. So first, let me establish the difference between a half adder and a full adder. So when we saw the half adder, if you can look at it in my previous video, so the half adder is actually going to add two bits. There are going to be two inputs, A and B, and each input is going to be 1 bit wide. So that means A can either be 0 or 1, B can either be 0 or 1. Then it is going to generate a sum and a carry. And in this, we saw that there are four combinations of inputs. The full adder, on the other hand, it is going to add three inputs, say A, B, and C, and then it is going to generate a sum and a carry. But we have to note that each of these bits, even in this case, is going to be 1 bit wide. So having said this, let us now look at the truth table for a full adder. Since there are going to be three inputs and all of this is being dealt in binary, so we are going to have 2 to the power of 3, that is number of symbols 0 or 1, and number of inputs, that is 3. So 2 to the power 3 combinations of inputs are going to be possible. So we'll have 8 combinations. So let's say A, B, and C are our inputs to the full adder. The sum and the carry are the outputs. So I have a black box, which is a full adder. I am providing three inputs to it, A, B, and C. It should generate the sum and the carry. So writing out the truth table, so we have to write out all of the 8 possible combinations. That's 2, 3, 4, 5, 6, and 7. So we have 0 to 7, 8 combinations here. The sum is going to be nothing but A plus B plus C. And whatever carry comes out of this addition will be put into the carry bit. And we have to remember that the sum bit is also just 1 bit wide. The carry bit is also 1 bit wide. So putting A plus B plus C here, since all of the three are zeros, this is going to be sum 0, carry 0. Here there's just 1 in the C. So that's going to be 1 with 0. Again, 0 plus 1 plus 0 is 1, carry 0. 0 plus 1 is 2. 2 in binary is nothing but 1, 0. So, therefore, I have to put the 0 of this 2 in the sums position and the 1 of this 2 in the carry position. Next, again, 1 plus 0 is 1, carry 0. 1 plus 0 plus 1 is again 2, which means sum 0, carry 1. This is again 2, sum is 0, carry is 1. This is 1 plus 1, which is 3. And 3 in binary is 1, 1. So therefore, I'll have to put a 1 in the sum and 1 in the carry. So the lower bit is going to go into the sum, the upper bit is going to go into the carry. So this is the truth table for my full adder. Now, I can identify the minterms. So if this is M0, M1, M2, M3, M4, M5, M6, and M7, and we know the expressions of each of these minterms, I'll just mention one. M0 is going to be nothing but A dash, B dash, C dash, and so on, right? So we can write out the expression for the sum and the carry with the help of minterms. So wherever the sum is true, I'm going to write that minterm. So it is true for M1, M2, M4, and M7. So M1 plus M2 plus M4 plus M7. This is the minterm that is going to provide the sum which is going to be true. I can write this in a simpler manner in this way: 1, 2, 4, and 7. Summation of this. So these are the minterms that is going to make up the sum. So when I write it in the expanded form, it is going to be a very long expression where each term is going to have three literals, because each of the minterms are made up of A, B, and C. So if I'm going to try and implement that using circuits, it will be a very tough task and is also prone to a lot of errors. So we can apply the K-map and obtain a reduced expression. In case of the sum with the full adder, we have three variables. So I will require a three variable K-map. So the three variable K-map, you can either write it in this manner. So let me draw the grid here. So the eight combinations. If this is A, here I can have B and C's combinations. So A can either be 0 or 1. B can take the values of 0, 0, 0, 1, 1, 0, and 1, 1. But we are not going to arrange it in that order. We are going to arrange it according to gray code. Now, gray code is nothing but this special code where one number and the next number differs from each other by just one bit. So 0, 0, the next could be 0, 1. The next one cannot be 1, 0, because the difference between this number and this number, if you see, both the bits are changing at the same time. So it can either go to 1, 1. That could be my next number, because this bit is retained and only the upper bit changes to 1. And then from 1, 1, it can come to 1, 0. So the gray code representation or the gray code sequence could be 0, 0, 0, 1, 1, 1, and 1, 0. 0, 0, 0, 1, 1, 1, and 1, 0. Why do we represent it using the gray code? This is so that we can apply the absorption law to the cells that are adjacent to each other. So, what is the meaning of adjacency, right? So, adjacency means that the cells should be lying next to each other, and they should have a unit distance from each other. So, putting together all of this, this is how the structure of my K map looks. I can number each of these boxes with the minterms, where the first box is going to be 0, 0, 0, the second is 0, 0, 1, the third box is 0, 1, 1. So that's 3. And 0, 1, 0 is 2. Then A, B, C in that sequence, right? Because A is my MSB and C is my LSB. So looking at it in that sequence again, 1, 0, 0 is 4, 1, 0, 1 is 5, 1, 1, 1 is 7, and 1, 1, 0 is 6. So this is our K-maps structure. We can now place the minterms as ones in these numbers. So there will be a 1 over here, 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 and here. If you look at this, you cannot form any groups because none of the ones are lying adjacent to each other. They should be next to each other. But that's not the case over here. This kind of a K map is called an odd function. So the solution to this odd function K map is an XOR, right? So it's basically the sum is going to be the XOR of all of the inputs involved in this K map. If you have an odd function, you can blindly say that it's going to be the XOR of all the three inputs involved in the K map. So the sum therefore becomes A XOR B XOR C. But how can we establish this, right? So I'll show you how you can simplify this. So here we have the first minterm, which is A dash B dash C. Why do I say so? Because uh, where I have placed this 1, A is 0, B is 0, and C is 1. So wherever they are 0, I'm going to put it with a complement. Without the 0, it's not going to be complemented. So in the same line, I can actually say that this minterm 2 can be written as A dash B C dash. Minterm 4 is A B dash C dash, and minterm 7 is A B C. Now I can take common over here. Like I can apply the Boolean laws over here. You might wonder why I am doing this when I have the K map. So this is just to show you that the odd function is nothing but the XOR of all the three inputs, right? So we can directly, when we see this brick wall kind of an arrangement on the K map, we can directly write it as the XOR. But I'm just showing you how you can say that, right? So this is the derivation for it. Here I can take A dash B dash C grouped with A B C and A dash B C dash A B dash C dash. So I've just rearranged the terms so that it's easy for me to take common. So I've taken C common over here. What remains is A dash B dash plus AB, and I can take C dash common over here and I get A dash B plus AB dash. So if we see, if I consider that this is X, this is going to be X bar. Why do I say so? So X is nothing but A dash B plus AB dash, which is the expression for the XOR. And the expression for X NOR, that is XOR bar, which is written as this symbol, is actually AB plus A bar B bar, which is what we have in this particular term. Therefore, I can say that this is going to be X bar. So now I have Cx bar plus C bar X. Looking at this term, again we can say this is the XOR between C and X. Now let me replace X over here. Then what do I get? C XOR A XOR B. So therefore I can say that the sum is nothing but A XOR B XOR of C. So even if I have a four variable K map and I have this brick wall arrangement, so say that inputs are A, B, C, and D, then the expression for that particular function of the K map is going to be the XOR of A, B, C, and D, right? So this is the expression for the sum of a full adder. Let's go on to see how we can find the expression for the carry. So I look at the truth table again and let me see what are the minterms that are involved for the carry. So that is going to be M3, M5, M6, and M7. So for these minterms, the carry bits are true. So let me write the K map again. It's a three variable K map. So for the carry, let me draw the grid with the 8 boxes, one for each minterm. The inputs are A, B, and C. And preferably, it should be in the order MSB to LSB so that it is easy to number the K maps and find adjacency and group. So this is 0, 1. Here I'll write out 0, 0, 0, 1, 1, 1, 1, 0, the four combinations that B and C can take, but in the gray code sequence. So this is 0, 1, 2, 3, 4, 5, 6, and 7. So the midterms for the carry were 3, 5, 6, and 7. So now if I look at the K map, I can see that there are some cells that are lying next to each other. Always we should remember that we can group the ones in powers of 2. So I can have a group of ones having two twos, that is 2 to the power 1. I can have a group of ones having 2 to the power 2, 4 ones, or 8 ones, or 16 ones, and so on. I cannot have a group of ones with 6 ones, or 10 ones, and so on. It's not even number, but powers of 2, right? So here I can see that there are three such groups that can be formed. So this is the first group. Now let me tell you how to write the expression for this, right? On grouping, first analyze the rows and see whether the particular input that is represented in the row is changing or not. So here if we analyze the rows, both the ones are spread across both the rows and A is changing from 0 to 1 over here, right? So A is not constant, it is changing. So this expression is not going to have A. Now let's analyze the column. It is stretched over one single column where B and C is 1 1 for both the ones in the group. So therefore, the expression for this group is going to be BC. Let's try another group. So here I'm going to group these two ones. This is my second group. So let's analyze the row. Both the ones are spread across a single row. Here the value of A is 1. For both these ones in the group, the value of A is 1. So this term is going to have A, and it is going to be ANDed with what is common along the columns. So let's analyze the columns. If we analyze it, it is spread across this column and this column. So this is 1 1 and 1 0. So if we closely observe, B is consistent at 1 for both the columns, but C is changing from 1 to 0, right? If we analyze these two columns. So whatever is common, we are going to retain it. That is B, not C, because C is changing. Let's try a third group. So here, this group, this is again spread across one single row where A's value is 1. So this expression is going to have A. It will be ANDed with what is common along the columns. So here this is spread across this column and this column. And here if you see, C is consistent at 1 for both these ones. So whatever is common for both the ones and it's not changing, that is going to be retained in the expression. So I have C also in the expression ANDed with the A. So these are my three terms. And the expression for carry, therefore, now becomes AC ORed with BC ORed with AB. And we have to remember that these are all AND gates. So this is the expression for carry, and this is how we analyze a three variable K map and write out the expression. If we see, there are going to be three AND gates and three OR gates involved in this. So it makes the circuit become very bulky. So we can simplify this, but for that we need to write out the minterms. So I'm going to rewrite this A, B, C plus A, B, C bar, because I've multiplied C plus C bar with the first term. C is the missing term. Then A, B, C plus A bar, B, C. A, B, C plus A, B bar, C. So I'm going to take A, B bar, C plus A bar, B, C, these two terms, and I am going to take these three terms and retain only one because they are redundant, and this one is what is left out, A, B, C bar. So now I can say that this is A, B bar, C plus A bar, B, C. I can take C common, A, B bar plus A bar, B. This is what I get from this. And grouping these two together, if I take A, B common, I'll get C plus C bar. C plus C bar is nothing but 1. So what actually comes out of it is just AB. So what are the two terms? It's AB plus this combination. And this is nothing but XOR of A and B. So ultimately I get my carry as AB plus C A XOR B. Now I'm going to try and implement it. So here I have A and B. These are my two inputs XORed. This is going to be XORed with C, and therefore I get my sum, which is A XOR B XOR C. We have to remember that this is A XOR B, this part. For carry, we need an AND gate so that we obtain A and B, and this is ORed with this. This is nothing but C ANDed with A XOR B. So I have A XOR B over here. This is my C and I'm going to AND it. After which I need to use an OR gate to combine the two terms. So here I have A dot B, here I have C dot A XOR B. I need an OR gate to combine this so that I get my carry. So if I look at it closely, I see that I have one half adder whose inputs are A and B, and the sum is going to be A XOR B, whose carry is going to be A dot B. Now I have another half adder, I'll call it as HA2, whose inputs are A XOR B and C. So the sum is going to be A XOR B, that's the first input, XORed with the second input of this half adder, and the carry is going to be the AND of the first input and the second input, that is C dot A XOR B, right? Because for a half adder, we know that the sum is A XOR B and the carry is AB. So we are considering that this is A and this is B, right? In that case, this is how we are going to get it. So therefore, now we can write out the overall carry for this full adder by using a OR gate with this carry of the half adder 2. So why do I need to do this? Because the expression for carry is AB ORed with C dot A XOR B. So I need to include this with an OR gate. So the AB comes out from the first half adder, which is ORed with C dot A XOR B, which is the carry of the second half adder. So this is the overall carry of my full adder, and this is the overall sum of my full adder. So that's all with this video. I hope this long video was useful to you all and you were able to understand how you can design a full adder using two half adders. And I hope you've also understood how you can group the minterms for a three variable K map. Thanks for watching. Please do subscribe to this channel.